So the plan for this kind of good final session of again presentations is going to be we talk a little bit about NPAR, how NPAR works and how to use it, and then also a little bit about dictionary indexing. I will not really be doing a full hands-on how to do dictionary indexing inside OIM analysis kind of thing, because honestly, it's not that it doesn't. I can't do it in an hour kind of thing. It really does take a little bit longer to do that. It'll probably be part of a how-to webinar, probably pre-recorded in some aspects, because again, you just can't. It's a little bit longer, and I'll talk about why it can be that long. So hopefully, right now you're seeing the NPAR presentation, and let's go ahead and talk about what NPAR is, again, how to use it, and how much I love NPAR, because it's made my life so much easier in so many aspects. And I got to tell you, I honestly kind of feel sorry for anybody who doesn't have an EDAX system at this point, because things like NPAR make difficult samples. It just changes the learning curve so much that it is an incredible useful tool for users of any level, from the most novice of novice EBSD people to again the people who literally write the code of how this stuff works. Is just an incredibly useful tool. So NPAR is a patented algorithm that we did. It's called neighbor pattern averaging and reindexing. The concept is honestly, it's not all that difficult. It's just that we take something like this. This is our grid. In this case, we're using a hex grid. It also works on a square grid. What we do is essentially, here you can see, this is, give me a second here. This PowerPoint is one of those ones where it's set up to like automatically go, and I can never remember how to turn this off. Slideshow maybe. Oh man, this is where, if anybody knows PowerPoint better than I do, this is where you step up and tell me how to turn off this stupid timing thing. Oh, there we go. Use timings. Don't do that. Cool. And then I got to switch this back over. There we go. So let me go ahead now, and I'm turning back on my little pointer thingy. So again, we use this hex grid concept, and this hex grid concept is something that we've always used. Again, our competitors don't use the hex grid. We use the hex grid on purpose. The reason we do this is the same reason that people do this if you play like, Dungeons and Dragons or anything else, is because this honeycomb pattern always gives you this equidistant center point. It gives you, it follows boundaries better. When you follow a boundary, it just follows things better. This is why we use it again. So we always kind of use this hex grid by default, and you can change that yourself. So again, to use this EBSD, used to have to kind of add gain and noise to your signal in general to go faster for the Hikari. Again, it's not quite as the same on the velocity. But of course, as you give this, you get more noisy patterns. You can get more noisy EBSD data for certain samples. In the end, of course, the really thing that matters is how well the Huff can find it. Again, we talked about this yesterday. Again, when you go from the pattern to the Huff transform to the index solution, what really requires here is finding positions of the diffraction bands reliably and consistently. So the real question here is when you're looking at this indexing performance, is some samples are just more difficult. So as you add more noise, this is what we call the indexing success rate. This is again how many grains are over that CI of 1. Over here is my noise value. So as I add more noise, you can see that as I add more noise, I start to have material that start to lose some things going on here. So here you can see here that the dual phase titanium, again, where I have 2 samples, it will actually start to drop quality relatively quickly as I add noise. If I go to something a little bit more easy, like a polysilicate silicon, polycrystalline silicon, it technically takes quite a bit of noise to really start dropping the signal. But again, how do I really kind of bend this curve? I mean, it's 2021 after the thing. How do I flatten this curve, right? I want these all to be nice and flat. How do I do that? And this is really kind of what I do here is, again, I can basically bend these curves by increasing a beam current. So for some samples, I can just increase the signal. I can increase the noise, but if I increase the signal faster than the noise, I increase the signal to noise ratio. But again, that's kind of a practical limit to how much current I can use. Again, modern microscopes often go up to 120, 200, or 300 nanoamps. If your sample can take it, sure, go for it. I also do frame averaging. Frame averaging is a little bit slow because it'll work, but it'll also basically take 10 times as long. So if I average 10 frames, it's going to take 10 times as long. So what we did is basically said, hey, if I take these 16 binary patterns, add them together, reprocess it, and run it through the entire thing, I can actually do this post-processing wise and increase my signal to noise ratio and to be able to do that. And that's just exactly what we did. So again, this is that old PowerPoint. This is not patent pending. We do have a patent on this. So this does allow, basically less time on the microscope and more time off the microscope. So you go ahead and collect your data, and then you get off and reprocess it. If you didn't have things like NPAR, you'd have to basically tweak your parameters over and over again on the microscope to make sure you got the perfect data set on the actual data set as collected. But because you can do this faster collection at lower beam currents and accelerating voltages, it's better for beam sensitive samples as well as better spatial resolution in general. Also, it just enhances data collected under normal conditions, right? Because you basically increase your signal to noise ratio, you get better data. So this right here is a good example of this, where we can see with traditional indexing, this is a very noisy data set. I go ahead and run it through NPAR, and I go from 11% to 96%. This is pretty common. I have a ceramic data set that I took for a customer. It's actually just pure noise. You can't even see the hint of a grain, and it comes out perfectly. It's one of the data sets I wish I could share with you guys, but I'm not able to. In general, this is kind of what happens as you increase your signal, your noise ratio. You add more noisy data, but NPAR is very easily recovered. So you guys can see here that there's no visible pattern really. In D, you do get some, you get indexing over here. You can see the grain structure in general, but it's very, very noisy. But with NPAR, it makes it perfect. Could something like grain dilation, CI standardization, grain dilation fix something like this? Yeah, it could, but we also would be losing some finer scale deformation features and things like that. Um, and this is again one of the main differences here between something like NPAR versus something more like the cleanup routines. For NPAR, the main thing to consider here is you are changing orientations, but you're not changing the orientations based off of sort of basically image processing technique. You're not just saying, oh, my neighbors have this orientation, I'm going to take that orientation and use it as my own. We're saying, oh, I'm increasing my signal to noise ratio. I am going to then rerun the whole thing through the reindexing routine to get a new orientation. And that is a big, big difference. So in the end, this NPAR will really do something like this, where if you take that noise level, it bends the curve and it flattens it, which is what we kind of want. Again, allowing for faster acquisition at lower beam currents, or just taking bad data in general. I don't want to kind of go over this too much, but it really does a good job. Here's a good sample of a rolled aluminum, heavily deformed. You tend to lose a lot of grain boundaries on something like this because of the deformation strength. And because of that, you only get something like 72% indexing. You run it at NPAR, you go up to 95%. So again, it really does a good job of bending the curves. Here's going to low beam current. This is a sample that was taken at 100 picoamps. Again, it gets noisy at that level because there's just not much signal, and because of that, things like NPAR do a very, very good job of cleaning it up. Yeah, I don't want to go over this too much. Here's a non-conductive sample. This is a good example of this, where with NPAR you can basically use less beam current and get the same thing. So again, this is 20 kV at 5 nanoamps. Charges too much. I actually go to 12 kV and 1.5 nanoamps. Run it through NPAR, you get good data. Sometimes I've done things that are incredibly non-intuitive with NPAR, where again, if I had something like this with 20 kV and 5 nanoamps of beam current, and it takes me a long time to collect it and I get charging, I've actually found the opposite can be true, where I will go to something ridiculous like 20 nanoamps. And what I'll do is I'll take my microscope, I'll go to an area and kind of do everything, pre-scan somewhere else. Then I will move to the area I'm going to scan and run it faster than I would using incredibly high beam currents, basically to basically outrun the charging. Because if I'm only spending, with something like the velocity, if I'm only spending, 0.3 milliseconds per point, my electron flux per unit area is actually relatively low because I'm moving so fast. I'm just moving away before the charging is a problem. So again, there are some really kind of non-intuitive things that you can use NPAR for. When you collect the data, I'll tell you, it looks like it's just bad, but you run it through NPAR and then suddenly magically it appears. Again, previously these samples would be something where I would have to run incredibly slow at low beam currents, and with frame averaging to hopefully get a data set, and that could be 10 to 20 times as long to actually collect that data set. And then of course it had to be run through iterations anyway, because to get to that level to see if I'm getting a good data set. So NPAR really kind of does save you time. And here's just kind of getting a deformed sample here, looking at again five nanoamps down to 1.5 nanoamps and getting the sample back. And this allows me to look at a finer scale deformation features. And here's again a good example of this, where you can see that the traditional indexing versus the NPAR actually gives you, in this case, it's called a local orientation spread. It's tighter because you actually get less noise in this area as well as the higher deformed areas. So it actually reduces, it actually improves orientation position and reduces your localized misorientation, which is kind of something that was counterintuitive to us. And of course, does show things like IQ better, but I don't want to really kind of talk about that. Okay, here's a tungsten stem. Again, it helps us with a tungsten stem, but I don't think you guys have a tungsten stem, etc. Here's a good example here of just a nanocrystalline polysilicon sample, which again kind of shows great kind of improvement. So that's NPAR, and again, you guys have NPAR on all your systems. NPAR does exist in team. You can run NPAR in team. In general, I would not do that. That said, NPAR is much higher. What's the word I'm looking for? The usability of NPAR inside of OIM Analysis has basically a much broader feature set, and that's why I run it inside of OIM Analysis instead. When we initially released NPAR, it was only inside of Team because it requires the indexing engine. It's one of the reasons we put the indexing engine inside of OIM Analysis when we went from OIM 7 to 8. So that's what I got here for NPAR. So if you have any questions on NPAR, now would be the time to ask. If not, I am going to move over to
Shawn, I have one question. In the spirit of what we were discussing as far as the cleanup algorithms, if you have that one slide, I know you just switched over, but where you talk about comparing the before and after running NPAR at different conditions, just wanted to ask how much of a difference it makes in terms of the consistency of the results, because there are different settings that you can apply when you reindex. And so does it make a difference in terms of the accuracy of the output as you adjust to those settings? Because you mentioned data faster. So let's see, go down a little bit on these slides.
Oh, it's not this data set. I don't think it's another one. I opened up a different PowerPoint.
Okay.
Should be this guy. Where'd it go? This guy or
11? Yeah.
Yeah.
So how much of a difference?
So go ahead and switch these back over. So this is a good example of this. If you can, we've actually done this. We have a paper on NPAR that actually does a pixel by pixel comparison. I think this actually is from that paper. So if you do a pixel by pixel comparison of this guy and this guy, this guy and this guy, or like this guy and this guy. So oops, let me go ahead and turn my actual pointer back on. So if you basically say that this right here is correct, right? So let's go ahead and say that every pixel in this guy is correct. And you compare the orientations from the NPAR of the incredibly bad patterns from this guy to this guy, they're essentially the same. So you're actually, you get a direct comparison pixel to pixel, will show you that this guy is the exact same as this guy. Is that always true? No, but for most data sets, you'll get incredibly good results. What I'll do with things like NPAR is, and I'll show you guys this inside of it. I use the FlexiView option to basically ground truth my data, where I say, okay, here's this pattern. Does this look like this orientation compared to something else that has the same orientation? And I can go, and I'll actually show you guys that as part of the as part of the uh, the other presentation, or as part of the live stuff. Good question. Um, but yeah, there's I think it's paper is called like the statistical analysis of NPAR and EBSD data, and we published that a couple years ago. Okay, so now we talk. This is 85 slides here. I'm not going to quickly do that. I also don't have this as PowerPoint, which is I thought I did. So this is from Dr. Stuart Wright. Again, his PhD was the one who essentially optimized and commercialized EBSD back in the early 90s. Again, we're very grateful that Stuart is still our main lead scientist out in Utah, and he basically OIM analysis is mainly his work. So all the coding and outside OIM analysis has been from him over the last 30 years. So just kind of a quick overview here of this. We can see that we have basically a pattern simulation tool has been added to OIM analysis, and that really allows you to do what's called dictionary indexing. I'm not going to talk about this other stuff in this presentation. There are some acknowledgments here. Of course, dictionary indexing is not something we came up with. Dictionary indexing was mainly from the Mark DeGraft group, and that group did a really good job of basically looking at this approach and seeing that it was feasible to do. But of course, to do the dictionary indexing, you have to make the dictionary, which means a lot of work has been done on the pattern simulation. People like Amos Winkleman and Mark DeGraff, again, have done a lot of work on basically saying, how do you model this to make an EBSD pattern based off of physics calculations? And they've done a very, very good job of that. So EBSD pattern simulations have gotten better and better over time. I also will tell you this is one of those good opportunities to look at things like pattern simulation versus the clarity, because the clarity allows you to basically test the physics because you're not dealing with anything that looks like the deformation or distortion based on the lens of the phosphor screen is removed from the equation. You're only looking at basically the electrons instead. And because of that, again, ground truthing the pattern simulations versus the actual patterns now is much easier based off of the clarity. I'm not going to cover too much about the pattern simulations. Just realize that there's math involved, and it's basically just scattering and making sure that you get coherent scattering out of a thing. In general, we used to use what's called the structure factor to kind of do this, but these don't always match. So this is a kinematic solution over here versus the experimental pattern, and you can see that there's bigger major differences here. And again, this is one of the main things that kind of drives this. So you can do this it's called dynamic simulations, which are again basically Monte Carlo simulations to look at how the electrons bounce around. And then when you do this through actual structure, you get what's called what we call the master pattern. We call the master pattern file. This is one of the reasons why doing this live isn't so easy, is that you have to build this master pattern file for most of your materials. We have built quite a few of these already, but these can go from like minutes to hours to days to weeks to build these when you deal with this. And what you do from this is you basically build a dictionary. You take this, you actually take this master pattern file. You then basically step your way through it through orientation space, and as you do that, you basically make a dictionary of patterns. And again, you have to do this through the entirety of this orientation space. So you can see there's a big difference here between these, the experimental and the dynamic actually look really close, while the old school, what's called the kinematic simulation, does an okay job, but it's not very specific for that. And again, you can see here differences here. There are still major differences between simulated and this. And this is, again, where we really want to understand with the clarity more what's going on. This is I'm going to kind of ignore. To realize that we have added this this dynamical simulation mode. Again, it's required for dictionary indexing because it is it needs it. So again, you have to build this master pattern file, and you can see that you can do this through this pattern simulation mode. And I think that's actually in OIM Analysis 8, but again, I'm not going to show the entire process. So what you can do with this dictionary indexing is you basically just have to sample the orientation space. Again, I'm not getting too much into the specifics because I study rocks. I don't study EBSD physics too much. But what you really do here is you start to compare these experimental patterns that you made, or excuse me, the ones that you've taken during your data collection, and then compare it against all of the dictionary ones. So again, you look basically, you're like, you can think about it as like a giant list of patterns, and you just kind of mathematically look through them and then compare them and see which one works best. Of course, the math here is basically looking at a dot product of normalized column vectors, but again, that's not what I'm talking about here. In general, when you do this, what you're doing is you have to kind of figure out what level you're going to make your dictionary at. And this is where the time really starts to build up. So I can do this dictionary at 15% spacing versus 5% spacing, or not 5%, or degrees. So 15 degrees, 5 degrees, or here at 2.5 degrees. And this is Rodriguez space. So basically, again, you increase the precision of your dictionary, but you're also your time to build the dictionary goes way up. And here you can kind of see this, that here's this kind of idea how many patterns you need at these different angular resolutions. So if you're dealing with a cubic and you're dealing with, half a degree orientation, you're still looking at, many, many millions of patterns. Well, here's a cubic one, right? The cubic one, you can see that, you're still dealing with about 1 million patterns at 1 degree orientation precision or angular resolution. As I go to something that's more like tetragonal, or me, of course, I deal with rocks. I'm doing this with like what's called the feldspar series, which tend to be more the orthorhombic, monoclinic, and triclinic series. You have to deal with upwards of 200 million dictionary basically images for your dictionary, and that's pretty crazy. So we can see there's a big difference here. So we did quite a few tests on this, and you can see that the dictionary does a relatively good job even on noisy. So here you can see as scanned versus with NPAR versus dictionary, you can see that dictionary can do a better job even on very difficult samples. So again, this right here is the data as scanned, absolutely garbage. You can't actually see a gradient structure, looks purely like noise. NPAR makes it okay-ish. The dictionary method actually does, gets it somewhere where it's serviceable. The dictionary indexing as of right now is not something you do on the fly. I think that's one of our goals, is to get it so it can be done on the fly, but you still have to have the master pattern beforehand. And here's a good example of this with the high green patterns. This is actually the example data set inside OIM Analysis. But you can see the dictionary build took 8.5 hours, or a little bit over 8 hours. Loading the dictionary took like 2.5 minutes, and then running it through the dictionary took about 20 minutes itself. This is a very computationally heavy process. This is not something you sit down, drink your coffee, sip it, and do it. It is something you set, forget, go do something else, because again, it's very computationally heavy. But as you can see, again, here's where your kind of your traditional indexing versus your NPAR. You can see that it moves it up. Can we do cleanup after dictionary or before? You can do it, probably usually you do something like that after doing the dictionary. Why? The dictionary indexing is indexing, right? So you can have your initial indexed data set and you can do that. But there's also a way to do what we would call CI selective dictionary indexing, where I can use things like that CI value as a basic filter to make it easier and quicker to run the dictionary process. And again, this is the kind of the big thing here is this dictionary spacing. You can see has to be relatively tight, because if it's not, you really start to run into problems with basically misindexing. So you do have to have this spacing in the dictionary, down to 2.5% or less. I will say that we are iterating right now on some of the further refinement of dictionary indexing, and Stu has done what's called dictionary indexing orientation refinement add on to this already, which actually makes this even better. So again, you can actually just kind of use a more coarse dictionary and kind of go from there. Yeah, again, these can take incredibly long periods of time. We've done, I've been doing this kind of stuff for geological stuff, and they are, are running me on the order of like a week. So which is kind of crazy. Don't really want to talk about this too much. Again, just realize that these patterns can be quite large. But it works. So again, here you can see where I can basically do this as selected as selective. So I can use a CI map, do something like the CI standardization we talked about, remove the bad data points, and then just use the dictionary indexing on those bad data points. So again, this is a case where I would not be doing a full cleanup. I would see something like CI standardization as a filter of what to do dictionary indexing on. Here you can see this actually works pretty well. This is that secondary kind of mode here. I don't want to harp on this too much, but I think that's pretty much all I got. But here you can see again, this right here is an extremely deformed magnesium sample. No matter what you do, this would always be a very difficult sample to run EBSD on. Magnesium is just a pain for EBSD. Here you can see as scanned, I'm dropping a lot of materials. NPAR does a little job of kind of cleans some of it up, but dictionary really kind of does a really good job. So here you can see the dictionary really kind of fills it in quite better. So this is one of those things to consider when you're doing this. So dictionary works. It has been implemented inside of OIM Analysis. So ta-da. One further aside, I did open up this presentation, did I not? Is I wanted to talk about parent grain reconstruction. Gosh darn it, this is annoying. So what is parent grains? Why does it matter? With certain phase transformations, again, I'm going to be probably skipping quite a few slides in this presentation. There are certain materials where usually via like heat treating or cooling, they undergo phase transformations as they do that. What happens is you have a what's called a parent or a child grain, where basically you have an initial grain and it subdivided itself into new grains. Again, this is what they call the parent-child relationship, and again, so you can kind of see that here. Let me go ahead and turn my pointer back on. Where here I have basically one big giant grain to begin with. As the phase transformation happens, you get different orientations based off of this. There's an orientation relationship between these guys back to the parent, and because of that, you can work this backwards in space and say that this grain came from an orientation and figure out that orientation. This is what we call, again, parent grain reconstruction. There are actually quite a bit of ways of doing this. There's a couple different algorithms. I'm not going to really kind of cover them in detail. We've actually been working on this kind of idea for like 20 plus years, and we've kept testing this and saying, hey, does this work? Hey, does this work? And we've never really gotten to the point before where we got results that were consistently good enough that we wanted to basically have it as a product to give to you guys as the end user. So here we can see that, this is basically, what my microstructure was. And of course, it is transformed over here to this guy over here. And what the parent grain reconstruction really does is says, I can use this orientation information to go backwards in time. And that's what this did over here. This is using what's called the Ranger algorithm. So that's kind of that one. The basic algorithm is relatively straightforward. You just basically do what's called a high confidence parent, and then kind of work back in time and say, okay, this grain here has got this. You can recalculate it, do an orientation refinement. Again, it's a little bit of an iterative process to do so. So you basically, again, you start off with your sample, and you work your way backwards or you work your way forwards by choosing the ones you think are best, and then do high confidence, and then do the lower confidence ones as you go on. Here you can see there's actually a couple different methods of doing this. Again, one of your colleagues there at Ohio State has his method over here, and we've kind of done, I think, a hybrid of some of these. I don't actually know exactly what Stu has done behind the scenes because this stuff is way over my head and how to actually implement it. So yeah, I don't want to cover that too much, but again, into this is one of those things where it does work pretty good. I don't think I really cover this stuff in general. Here's a good example here of this kind of parent grain reconstruction, where you take again, in this case, a Ti-64 sample that was an AM material, and go ahead and run it through this kind of algorithm. It's very this is where the velocity really kind of helps. Because you can do large area mapping over with incredibly fine scale, fine scale step sizes. So here's where you can see you have 2% retained, in this case, retained beta phase, and you can use this as part of it. Here are the beta phanes but you actually can reconstruct this out of that. So here you can see the reconstruction. So this right here is the as scanned EBSD map that after it went through the phase transformation. This right here is the reconstructed basically data, and it actually does a good job. So skip a couple more slides here and basically say that again, there you go. So here you can see that how we basically turn this parent child grain into basically a single parent grain, or you can use this for your grain size determination. So now this exists. Again, this is a brand new concept to a commercial EBSD. Again, it existed in the academic world for a while, but again, we've never actually been happy with the results we've gotten to do that. So there we go. Now you know everything about dictionary indexing and NPAR and parent grain reconstruction. So at this point, I am going to close PowerPoint, and I am going to move back over to our good old friend OIM Analysis. And I hopefully cleaned up more room on my hard drive. I was down to like 300 meg of hard drive space because, again, I do EBSD for a living, so I absolutely bury myself in data. So this is my high gain nickel sample. Go ahead and open this up. Go ahead and open up FlexiView, add EBSD pattern flyby. So now I can see the patterns. Go ahead and apparently I don't want to full screen this. Okay. That's going to be annoying. This bar is going to be bouncing around here for a while when I do some things. So to do any sort of data reconstruction or reindexing, I had to click on the magic beach ball here. This is the reindexing thing. So I click on this, and then I click on my sample here, and it opens up the data set. Now, this is essentially the general workflow up here is kind of this, right? So you work through and you're reindexing this. So I'm going to go down here to image processing and turn this off. This is the data as collected. So what I'm doing this kind of thing, what I'm actually going to do is do image processing on the patterns as collected to make them better. So here is the pattern as collected. I can now do a background correction here. So if I collect the data, I use the scan speed to basically collect multiple frames and average those together as my background. I can also just use my data set that I have as my background, and that allows me to do this. So here I can do what's called a data set background correction. This will take every single data point here. So now you can see basically removed all of the the background signal that I had. The other way I could do this is what's called a partition background correction. What that means is I can make a new partition over here, and then I can use just the partition that I have as my background. So again, this is a way for me to make a selective background based off of maybe a phase. Why would I want to do this? Again, I come from the meteorite world. I'm dealing with samples that will have a very low Z silicate phase versus pure iron nickel material in it. So if you try to do EBSD on something like this, what can often happen is getting a good background is very, very difficult because I'll have the high Z material and the low Z material are very different signal strengths. So if I try to subtract a background from that low signal can actually get even lower. If I do this on a partition-based approach, I can actually make it so that the background is basically the material. And if I do that, I will basically not suppress signal from the low Z material as much because again, I'm using the Z material as its own background. And this is again where I find this. I have a webinar where I show you guys how to do this. I think from a couple years ago, and I forget exactly what it's titled, but it's actually using this partition-based approach. So now I can do things like what's called NPAR. And this is actually, we've kind of changed a little bit, but this is the basic NPAR. So you can see I'm doing NPAR here. So this is the power of NPAR. I turn this pattern here into that pattern there. And you can see it changes the orientation a little bit. So this is a better pattern. This will give me a better data, less noisy data. And again, I turned this as collected pattern into this pattern. There are actually more options here. Again, I have a whole bunch more things that I could do here with like auto zoom or barrel distortion corrections or sharpening filters or other backgrounds. Again, I can do a whole bunch of stuff with these backgrounds if I wanted to. But in this case right here, this is kind of what I usually do is either a data set background or dynamic background combined with NPAR. And from that, I can also add or remove a phase here. So this is where I can say, okay, this is not nickel, it's ferrite or whatever. I can go ahead and add and remove this as a phase. Often what I'll do is something like this is I will just, again, I will just have multiple phases here and I'll say just don't run it. So indexing parameters, again, these should look familiar. This is where I change something like the interplanar tolerance angle, where I can say use fit ranking or don't. And of course, here's my calibration. I find this calibration to be incredibly useful. This is a good way of kind of like tweaking for that stuff that is not accounted for as you do an actual scan, right? So again, we talked a little about this yesterday. When you mount a sample, you have your slide or you have your stage at 70-degree tilt. Then you have your pin stub in there, and then you have your sticky material, and then you have your mount. There's a lot of wiggle room built up into that system, which means your actual angle may not be what you think it is. It might not be that 70 degrees. It may be 71 or 72 or maybe 69 or 68. That can be seen in your data. So here's where I can actually go in here and actually tune for this. And it'll basically make this pattern fit better for that. So this is a kind of a secondary calibration I can do to correct issues from the actual system itself. There's also where I can change my Huff transform settings. Again, I told you guys yesterday that I often have my vertical bias a little bit higher, and here you can see exactly that. I usually have it at 3. And this is, of course, where I can change things like the theta step or the rho fraction. Again, this is not being live, so again, I talked yesterday where the velocity needs 2 degrees to run full speed. In this case here, I just kind of keep it at the default. So here's where also you can see these convolution masks. Again, I think I had a question yesterday about the second pass filter. Here you can see it is. I keep it at none. There's really no reason for it to use it for general things. So this point over here, this is really just kind of doing what I want. So if I look over here, this is going to be my index solution. This right here is the Huff lines that it found. And of course, these should match. So this is a good way, again, I talked about this yesterday, is how can I tell that I'm getting a good index solution? This is not the best example, but if you look right here, there's a line right here that the Huff is not using, which means it's not being used for the actual indexing, finding the indexing index orientation, but we can see that it is there. So this line right here is saying, hey, this orientation is correct. Now, if I go down here, I can basically say, hey, just reindex this single point I took. Now, this is not a huge data set, but I don't think you want to go ahead and click on each one of these and double check everything. So if you click on this button right here, it's go ahead and reindex this entire partition. So again, I did this partition. Right now, my partition is my entire data set. If I separated this partition out and did like just a lower CI area, then I would just be having that, be running that. And this guy lets me do batch mode. So I talked earlier about batch mode. This allows me to basically run NPAR on like 10 scans at once. So I can just set it back and let it do its thing. In this case right here, I just kind of click on reindex partition, and you can see it's reindexing. Here's my CI through time. Here's my pattern. And also I can see how long this is going to take. This is going to take around 2 minutes or so. So here you can see that this is an artifact, by the way, of basically your screen, how you have to shrink some things down. So this is an artifact of actually Windows code. So here you can see, again, this is a big grain, right? So this is grain up here. It was very noisy. Now you can see there's no noise in it. Again, these twins are nice and clean, and my CI is very, very high. And about a minute into this. Now, something I won't do, but again, I could go over here and say, hey, only give me the bad data points, and then I could do the CI just on the bad data points. Any questions, comments? If not, this is where we hurry up and wait. You get to watch a green bar move. How's that for exciting content? It's the thing about science, right, guys? Is that so much waiting involved. I always tell my wife about sciences. My background is actually very strongly chemistry. I used to be a trace element and isotope geochemist. So the thing I always tell her is that I'm just a very well-trained dishwasher, because that's all you would do, right? Is just wash dishes very cleanly. Now she asked me what happened to those skills, and it's like, well, I'm a little bit more tolerant for contaminants in my food apparently than I am for my geological samples. I'm not sure what that says about me. So there we go. It's done, and I can go ahead and open up the data set now, and you can see that it's much better. And of course, again, if I close all these windows, click on them, put them side by side, you can see the differences. So again, some of the things you can be worried about here is, what is this changing and what should I be actually be concerned about? But this is also a really good example of what NPAR can do well. So you may not be able to see it very well on your screen, but you can see there's a color difference here, right? There's a very subtle shift from here to here, and you can see that there's a kind of a little bit of deformation here. This is real. So we can see that this deformation here is basically in the sample, and it's completely lost in the noise here. So very fine deformation is still seen even after running through things like NPAR. And the same thing here, you can see there's deformation here. That said, you can lose some very fine level features. If you look like right through here, we can see that there's a twin here and we're losing it. And the reason we're losing it is pretty simple, right? Is because if I had let's say I had a 1 or 2 pixel area that was made up that single twin, if I use NPAR, NPAR can push that boundary over on both sides. And then suddenly that thing that was 2 pixels wide is now gone. That's actually exactly what happens here. Also what happened here in this case, where again another grain boundary is lost. But here you can see this one right here is about 3 grains across, and it's not lost. Now, I actually kind of told you the solution to this in general. If I know I'm going to be doing some NPAR later, I will often kind of make my step size just slightly smaller so that, again, I'm not dealing with this. So I told you earlier that I usually do things that are, if I know the general grain size, I want to be, my step size about 1/10 of that. Well, that's kind of it's a slight missaying of what I should say. What I should say is I want my step size to be around 1/10 of the feature size that I most care about. So in this case here, if I was trying to figure out, hey, what percentage of twins does this material have? This is bad data, right? I basically this is gone. So in this case here, if I made this, if I went and took this data set and I recollected the bad data, so to speak, at a finer step size, I would be able to see this this twin here, and I'd be able to basically account for it if I was trying to get the total amount of actual twins in the material. But again, in this case here, maybe I don't care about twins, and this is fine enough for what I'm doing. Anything else to really kind of talk about this reindexing? I really want to talk about, let's go ahead and do filter base. So here I go up here. So this is that high data set. I go up here, make a new partition, and I get I want the bad data points. So I want CI less than 0.1. Oops, wrong area. I want to put that here, 0.1. Click on OK. And now it's going to basically filter out all the good data points. So now I have this this new data set up here, this new partition. I go ahead and reopen it, and it's did I do that backwards? Oh yeah, I forget this data set's really just that bad. I want to change this, maybe change my properties here, the CI to 0. Oh, this is actually going to make it worse. It doesn't really matter. This is a very bad data point. So I'm showing you the bad data points, but you can see here it's kept some of them. That's because I'm doing this in the wrong order. What should I do first? I should always do CI standardization first. So I go back up here, click on cleanup, click on CI standardization, click on OK. Now it's going to hopefully get rid of most of that bad, the good data, so to speak. So this right here is now CI standardized. How can you tell it's CI standardized? If you look down here, there's a status bar. You can look right now, you can see that there's a CI of 0.19, 0.19. It stays steady in all the correctly indexed points. So now if I filter, or if I partition this, and I go new partition, only give me the CI values that are less than 0.1. I might not have been click on the right one up there either. Click on OK, OK. Now I should have only the bad data points. You can see the bad data points tend to be around grain boundaries because that's just kind of usually what happens. So now what I could do is I can just run this through NPAR. Now, again, this is not a huge data set, so it's not going to save me that much time, but go ahead and click on here, it opens it up. I make sure that I have the image processing on, so NPAR and data set background, and then I go ahead and rescan it using the button over here again. It goes, a little bit quicker because I'm not redoing all those data points. So basically, again, what I've done here is I have said, okay, I've done CI standardization. So basically, I said that, by CI standardizing the data, I'm basically saying, hey, this data was good enough, don't change it. And now I'm basically just selectively re-indexing the bad data points. So now we're about halfway done. Again, here you can see it's kind of looking like doing the outsides of the data set in this case, and you can see it looks a little weird because again, this is the good data, so to speak. This is the good data it had, and now I'm filling in again the stuff that was not so good, usually around the outside of grains or in the inside in some cases. When I'm doing a partition, I'm actually not like throwing data away. The stuff that is there is still there. It's just basically not showing the data, or we're using it as part of any sort of like statistical calculation. But I have the ability to basically turn that data back on. So here we can see this is basically finished up. I go up here, click on this scan, and ta-da. This right here is that data set run through NPAR, but only cleaned up the data that was basically bad. So again, I can do this for different phases. I can do this for different whatevers. The other power with this is the fact that, again, if I can do this on different phases, I can actually change my Huff settings per phase. So if I go back over here to this Huff transform, and let's say I had like, maybe a hex-based titanium, I could say, okay, for this hex-based titanium system, let's go ahead and use more bands. So now I should feel a little bit more comfortable with my hex-based system because I'm using more bands, but I'm also not using those bands for my cubic system, because what can often happen for a cubic system like this is if I try to have it find 12 bands, are there actually 12 bands to be found? And here's actually it can. I mean, this right here is probably the one I have the most questions about, but I think it's real. So you see now I click over on this Huff, and I was trying to figure out if, which one is it? Which one is it? Now you guys get to watch me figure out, oh, it's this one. So it's basically saying, is this one here real or not? And I don't know, that one's pretty subtle to me. I'm not sure this is actual a real band, or if it's because I made it try to find 12. It's like, oh, hey, this is this. You can always do 20. If I do 20, it's definitely gonna have some bad ones, right? So it's like this guy over here. I don't know if I believe all these, but it's gonna use those index because I told it to, right? So again, this is one of those cases where, hey, this is too many bands. 12, again, I'm not convinced that this guy's real or not. Honestly, if this indexes this, it's going to be fine. It's going to be able to figure it out. I'm trying to think, what else do I want to, what else do I want to show for the re-indexing stuff? I mean, the basics of the, just in case you do want to do tutorials here, the basics for the, oops, that's not what I wanted. The basics for the dictionary index is this down here. Again, it's just a pull down. In this case, you also hit F10. You're gonna have to then build a master pattern file. That master pattern file is gonna be built using this guy up here. So this right here is how you build this guy. So you can say to, hey, go ahead and do a do the thing here, and it'll run through it and build the dictionary for you. But again, this is covered more in tutorials, so I don't want to do that. It also takes a very long time. And then, of course, you'd use that dictionary here. Where you actually would load that dictionary, find the dictionary, because I don't actually have nickel on here. I should probably make a dictionary for that. And then from there, it would basically, this is where you can set up this to use the dictionary. The other thing to really kind of show you at this point is going to be chi-scan. I have to use chi-scan a lot. Again, I'm a rockologist. And what do I want here? I just want, yep, give me a minute here. What sample am I looking for? I am looking for this guy. So this is one of the demo data sets. This is a good example here of why do I need chi-scan. This is an interconnect that has this. In this case here, it is used austenite to index it, but it's not austenite. How can I tell? Well, if I have EDS data, I look at the EDS data, and the EDS data is going to tell me kind of a different story here. So right now it's loading in the EDS data, and I look at the EDS data, I can say, wait, there's copper here? And you'd be like, wait, what? So copper is not going to be austenite, but copper will perfectly be happy to index as austenite. So this is one of the main kind of things you have to consider with the EBSD data, is that if the phase is close enough, it'll index. So in this case, copper and austenite are essentially the same lattice parameters and crystal system, and because of that, it'll index as austenite. But if I wanted to get the phase, so I wanted to see, hey, is there a difference in the grains between the copper and the interconnect? What's the grain size here? Do I want to engineer the grain sizes to be different for some reason? Here I couldn't do that. I would try to make a grain size chart, and it's just going to be all the grains. It doesn't help me at all. So right now I click on this guy and say, hey, this is going to be again, this is garbage. It's two phases together. I know it's two phases together. This isn't actually telling me anything. So what I can do in this case here is I can use my little magic beach ball, click on it, and it's going to load in the huff peaks. In this data set, I don't actually have saved patterns. I only have saved huff peaks. Why does this matter? Well, if I only have huff peaks, I basically have to say it did the huff right the first time, right? So I can't do image processing on the huff. It doesn't exist. But what I can do is I can go down here and do what's called chi-scan. And this is basically just chemistry-assisted indexing. And that's the evidence you needed that I'm running a beta version. So what this does is basically says that, okay, I can see I have different components here. I have iron, nickel, and copper. And what I can do with this is essentially say, hey, find the components, and it will automatically basically figure out what components I have that differentiate between what's in my sample. So right now it's looking at each pixel by pixel and saying, okay, doing a basic principal component analysis, how are these pixels different? And this takes a minute because again, it's doing all pixels and it's looking at all the things going on. I also can, in this case here, I can block these together. I can change the tolerance level, and that just changes how the PCA basically says, hey, is this a new phase or not? So as it does this, it's basically, again, it's just going pixel by pixel by pixel. I also could use different things down here. So here, if you look here, you can see where it says PB, PC, PT. That's Prius. So I actually can use the Prius image as part of this and say, hey, if I clicked on down here because I clicked on Prius, I could use the Prius as part of this principal component analysis. I did not. The reason I did not, as you can see, is it's doing a lot of work computationally. In this case here, these aren't really telling me anything. When do I use things like the Prius on this? I have found it to be useful for things like for martensite. The channeling can be just different enough, and the carbon content different enough in martensite that things like Prius or the IQ image will see that. If that's the case, I can actually use that component as part of the PCA. So in this case here, I look at this, I can see that I have this red phase, and this red phase is austenite. So I say, okay, this red component I'm going to reindex as austenite. And then I click on this yellow phase down here. It says, oh, this yellow phase here is copper. And I go here and it says, wait, I don't have any copper. I can go ahead and load it though. So I go load PC, OSC, or not OSC, C drive, program files, TextSem, OIM Analysis 8, materials file, and I find my good old friend copper. I always forget if it's COPPER. There we are. And click on OK or open. So now I've added copper to this list and said, okay, let's go ahead and do this with copper. So here we can see that, there's 63% of my area here is this red, and I'm going to index using austenite. This right here is using copper. Of course, if I actually have multiple phases, I can use multiple phases here. So I can actually load up and say, hey, use both these phases here if I wanted to. So if I did have a geological sample where maybe the EDS data was still similar, I could have it also indexed using multiple phases. And in the end here, I click on go, and it's going to do this relatively fast because it's not much data in this case. So it's reindexing it based off the CI, or not the CI, the EDS data, and of course those new phases. If you look very carefully, you can see there's actually a little bit of a nickel segregation here. Those are those other phases at the bottom there that did not add anything there. So it's not reindexing those. It could basically tell it to ignore that as well, and just put the data back up as it was. So it's just one of those things to consider if you really want to do this kind of thing. So here we go. Again, CI is nice and high, which is good. It's going to be the same no matter what. So here's my CI, almost done. Well, the next thing I'm going to do, by the way, is I'm going to ask you guys a question because I'm going to mess something up on purpose. So here I can see my IPF image is actually exactly the same because there's no real differences here. Again, this is a nickel area, redo that. But now if I click on this, I can see that I have an austenite area and I have a copper area. And now if I wanted to, if I click on this, something like this here, click on the austenite and I click on this, I'm getting the grain for just the austenite grains. So now I have these bigger grains here with the smaller grains. So I can go ahead and look at the grain size distribution here of this. And I can also do the same thing for copper. Okay, now let me go ahead and do something wrong on purpose. So this is going to be that initial data set. I'm going to click on here. I'm going to go down here to phase. And I'm going to say, let's not just do austenite. Let's also add copper. So now I'm going to tell it to use both austenite and copper to reindex, and I'm going to go ahead and have it reindex. And what's the big difference? Oh no, my CIs are red. Why are my CIs red? Any idea? Let's see how much people paid attention yesterday. So now I've added copper and copper and austenite are both being indexed at the same time, and now my CIs have gone bad. Why is it bad? Who gets an EDAX brownie point?
If anyone wants to answer, just answer in the chat real quick as well.
There we go. Somebody answered.
There you go.
So no, it's not the wrong phase. It's not the wrong phase. Well, it is not the wrong phase, right? Because both these phases exist. The issue is that the two phases are essentially the same. So when it votes, the votes are the same. So if I actually stopped this and went down to solutions, and how do I do this again? There's a way to do this. So phase, both these are being done. And then I always forget index. So now it indexed. And go back down to the solutions here. You can see it has the copper and the austenite here. it has 35 votes. It has 35 votes. So now if I take solution A minus solution B, I get 0. So 0 divided by whatever number is going to give me 0. So because of that, again, this is always going to be 0 because these phases are essentially the same. That's why, again, this is why Austin by itself worked, is because it is basically the same phase structure, and because of that, it works fine. But by adding copper and doing chi-scan is actually pulling those apart and saying only use the copper phase file for the area that has copper, and only use austenite for the areas that have nickel. So, anything else I really want to show at this point? I mean, other stuff for this is I mean, there's just so many options. I could talk about OIM analysis for weeks, but trying to think of anything major that I've missed kind of talking about. Anybody interested in like texture analysis? I mean, that's one of the things I haven't really covered.
Hey, Shawn, before you move on to that, I was wondering how you run these experiments well on the microscope. So experiment I was doing a while ago with EDS, EBSD. We're looking for small concentration of something large area on using a velocity camera as well. So we're at high currents tilted to 70 degrees. I was practically getting too much signal, had to back off my detector. But then I was running so fast, it was only a few counts in the areas I was interested in. Do you normally like try and just slow things down a lot then,
Yeah.
just speed wise? Or I don't know, that might be a spot where the velocity is actually not as useful because you need the counts to get there.
So one, I would yes, I would slow down. So in that case, the first thing I would do is go out of super mode. Because again, super mode has that mode where essentially again it's using the higher range, but it's easier to saturate the camera. So by going out of super mode, you would now be on the lower end of the range, which gives you more range to go higher. Does that make sense? So leave super mode, go to the normal mode. The other thing there again is I would just kind of um, I would slow down. So in this case, um, I would go to a lower you basically go slower EBSD collection to get more EDS counts, because usually it's kind of crazy when you actually do the math, right? So when you do like combined EBSD EDS, let's say you're looking at let's pick a nice round number here, and I'm going to mess this up because I somehow always mess up this math. But let's say we are doing 0.25 milliseconds exposure time per frame for the EBSD camera. And let's say my EDS detector is doing 400,000 counts per second. How many counts per pixel am I getting? So when you actually do that math to see, okay, 400,000 counts per second, I'm doing, let's say it's basically I'm doing 4,000 patterns per second. That means I'm getting 1,000 counts EDS wise per pixel. But then you have to do the math a little bit further, right? So that's 400,000 counts is quite a few EDS counts. If I'm getting all those input counts, how many of those input counts are being thrown away? Well, again, so let's go ahead and cut that down. So now if I'm dealing again with this 1,000 count EDS spectrum, 10 or 20% of those might be actually thrown away just by dead time correction, right? So, those are being thrown away because I'm running at this really high speed to begin with. How many of those are background? Okay, I start looking at that. It's okay, how many of those are background? Then if I have like a multi-element sample, how many of those are going to be other elements? So suddenly now your 1,000 counts per spectrum is like 5 or 6 counts on peak for the EDS signal. So you really have to be cognizant again of how many counts you're actually getting through that are being included in the actual EDS signal itself. Does that make sense? Again, this is one of those things that I run into all the time where I do EDS data, where it's just so sparse It's crazy. I do data like all the time on this where my EDS spectrum will be like 3 counts per pixel, and it's actually the same thing with even just EDS maps in general. As people collect them too fast, even at high count rates, your counts per pixel is just tiny.
Yeah, no, it makes sense. That's kind of the struggle with that part of the project, was looking as a small concentration of something we're trying to look for a large area where there'd be some grains with it possibly. So,
Yeah, this question about this question about making new partition for each phase will do the same purpose. Yes. So if you do the partition based off not the phase itself, but the EDS, you can do that. So if I went up here to like this guy here, and I did new partition, and I said, so let me do the EDS data open. I do, so like right here, I have my copper map. This might be a little bit difficult to see again. So down here is my status bar. Hopefully you can see the very bottom of my screen. What I can see here is that in my copper area, if you look at my copper signal, it says 475 counts over there on the left-hand side. So it looks like in general, I have about 400 counts per pixel in my copper areas. So I could go new partition, only give me the areas that have our EDS counts for copper greater than 400. And now again, I've basically done the partition based on the EDS data. I can't partition it on phase directly because in this case the phase is going to be from the phase map, right? So if I went here and said partition via the phase, I only collected it as austenite. And again, it's just do that. Now, if I actually collected this data as austenite and copper, it's just going to be kind of a jumbled mess because I can't tell the difference. Good question though. And this is one of the things again where I couldn't even really do this before adding the indexing engine inside of OIM Analysis. And this is actually an unintended consequence of being able to do this kind of partition-based indexing approach. This is again something that when I found it, they were like, "Oh wow, that's pretty neat." And I was like, "Yeah, you guys made it. You just didn't realize you made it." Trying to think of anything else that I really want to talk about. Do talk about. We'll talk a little bit about texture analysis, but one quick other thing about chi-scan. What I showed you was chi-scan using what's called principal component analysis. If you turn this off and then click on chi-scan, you basically set the thresholds. So you look here, this right here is like, this is the austenite phase. Again, I actually add the copper phase, but I can say that for the austenite phase, here is my, where's my iron? My iron's over here. I can say, okay, this is my iron map. I can say, here's my lower bound, here's my upper bound, and you can say, hey, there's that. So here you can say, basically the same thing. And then this is a little bit more tricky because it's tiny, but I can do this. So right now I'm basically saying only use this. And again, I can have this here. I can say use the Prius signal. This is going to be bad, I think, but drag them in. And I can say, hey, these are kind of my bounds that I'm setting based on this. I honestly usually use this for geological samples because it's a little bit more, it's quicker to be honest with you. Because with the PCA, if you have like a 5, if I have a sample with 5 mineral phases in it, and those mineral phases share 3 EDS signals, but they also, the actual component that matters is a trace element. Doing the PCA and pulling those apart is very, very time consuming. So it just, it's one of those things. Okay, can you talk a little bit about texture analysis? Yes, I can. I will tell you that I am not a texture guy. I know how to do texture analysis, but if you ask me that, say, hey, why exactly does this texture form? And you'd be like, oh, well, it's a whole series of, stacking faults in the 111 or whatever. That's beyond me. But let me go ahead and open up a textured sample. I always forget which one of these is textured. I think it's the aluminum that has a very strong texture. At this point, by the way, I'm using one giant OSC file. If I was smart, which I am not, I would probably save and open up a new OSC file at this point. But again, I just told you I'm dumb, so I'm not going to do that. So this right here is an aluminum film. If we look at it in general, it feels like it's texture because it's very strongly blue. I often go down here to this lattice. You can see that there's a relatively strong texture to it. So you see how the point tends to be towards me. This is textured. So to do a texture, you have to make an intermediate file called a harmonic. So to do this, we go down here to this texture, and then we basically walk through it what we want it to do. So in this case here, I say I want to do, for the aluminum phase, I want to do what's called a harmonic series expansion. And then I wanted to do the harmonic series expansion for these kind of pole figures. So there are also what's called discrete binning or the harmonic series. This is where I start to get a little bit over my head. The harmonic series expansion, my understanding, is the way to go. The discrete binning method is basically a little bit more error prone and a little bit more of a very fine cutoff, so to speak, of what it's doing. And because of that, you tend to get a little bit more artifacts. The harmonic series expansion takes longer to do, but at the same point, it's more of an indiscrete kind of curve instead of a kind of a chopped up curve where it kind of just picks up where it's going to chop it off at. So I'm going to do a harmonic series expansion. You can actually change these values. Don't. Again, unless you really know what you're doing. This is the series rank. If you make this larger, the computational time goes way, way up. Of course, you can save time by basically using a subset of your points instead. So this is saying use all the partitions, use n random points, etc. So again, it can be smart enough to basically do a kind of a statistical sampling of your data if you wanted to. And then down here, you can see it said, okay, do a pole figure, do a 001 pole figure using 5-degree binning. I also do the same thing with all the inverse pole figures. If you're looking at texture, you should almost always do all three, both the 001, 111, and 101 or 110 or whatever, and do that. Here's also where I can add things like an ODF, and an ODF is something else I can do. Again, you usually have no real reason to change these, and say, okay, so right now it's saying build a harmonic file for the pole figures that I just did, the inverse pole figures, as well as the ODF. There's also where I do like a fiber texture. So here I can say do a fiber texture for alpha FCC rolling or beta CCC or whatever you want to do up here. In the end, you click OK. When I click OK, it's going to start doing a lot of math. So now we get to watch paint dry. And it should take that long, actually. So right now, it basically did the basics of the binning, and now off of the binning, it is doing the ODFs, the pole figures, as well as the inverse pole figures. So now I have this harmonic texture up here, and off of this, I can build these detector plots. So now I can say, okay, go ahead and show me these three. And now when I do that, it'll show me the inverse pole figures of those three. Yeah, and this is where, if I was lazy, now I can see that, hey, this has a 1-1 texture, which we already knew, right? Because I actually looked at it, went back to Flexi View, it has a 1-1 texture. And now I have math to show me I have a 1-1 texture. So this right here is a 1-1 texture. Again, 1-1 texture, looking at it from a different pole figure, a different direction. How do I read these is a question I often get. And the scale for these is what I would call slightly counterintuitive. It's not counterintuitive, it's just a different way of thinking. So the scale from this is usually from 0 to some value. The value for the maximum value here is always going to be basically, again, how strongly textured your sample is. And what this is basically times randomness. And what that means is that in a perfectly kind of, what's the word I'm looking for? A non-textured sample where my orientations are perfectly random, my sample would be basically green. So it's basically saying that I don't have a texture. All my orientations are just randomly distributed. Of course, if I have a texture, then I'm going to have an area where I have more points than should be per unit area, right? So this right here is a good example. This is all my figures here kind of go around here. So these are higher. In this case here, this is in this range here. So it's 3.5 times to 5 times randomness. So there's 5 times as many points in this area as there would be if it was randomly oriented. And of course, it does the same thing for the inverse pole figures, which, if you ask me, are usually a little bit easier to kind of get an idea at if you know what you're looking for. So here's the inverse pole figures and say, look, at the one-on-one texture. Of course, again, these are telling you the same information, but oops, darn it, I clicked on it to rename it. So again, here you can see that this does. I know this is a one-on-one, right? So it's like 45 degrees in. This right here is the one-on-one, but in this case here, it's basically screaming at you and saying, "Hey, look, I'm the one-on-one." It's also, again, it's a little bit, it it brings down the pole figure into the inverse pole figure space, and because of that, it's a little bit more crunched. These are also easier to see if how things are moving, right? So if you do like roll something, you can see that often it'll basically it'll follow certain. This is where I always use wrong words because again I'm slightly out of my depth here. But if you have like a rotation here, it'll work its way towards this one-on-one following certain paths, right? So it'll go like this, or if I had a grain over here, it'll go like this as it deformed towards a certain texture. So that right there is again the basics of texture analysis and using this. Again, interpreting that, I leave it up to the end user because that's just not me. Yeah, there's a lot of yeah, texture again is a little bit above my pay grade, so to speak. Any other questions about this kind of stuff? Anything I might have missed that you might want to see in OIM analysis? It's like, hey, can it do this? Hey, can it do that? Honestly, the answer is almost always, yeah, it can do that. If not, if it's a good idea, we often add it. I do know there's a customer here in our chat here that we've done a lot of individual work for to add stuff for them. So again, if it's a good idea and it works, we tend to add it. We also tend to add it relatively quickly. Our software guy on this stew is like, oh, it's a good idea. And then if he really likes it, he'll dive into it, and suddenly I'll have a new build in my hard drive by like the end of the day with that. So at this point, we're at about 11:50, which is almost lunchtime, and I kind of showed you everything I wanted to for this. So again, if you have any questions at this time, this will be time to ask. If not, we'll kind of break for lunch, and then after lunch, we pick up at 1 o'clock. And at 1 o'clock, it's basically I want questions. So it may be a short session, it may be a long session. I don't care. I just want questions from you guys to make sure that all the questions you guys have on basically anything to do with EDAX can be answered. So the only thing I don't have questions for is how much does stuff cost, because I don't know that, because I don't want to deal with that. I only deal with what it could do, not how much you have to charge us or how much we pay for it. So no questions. Giving you guys another 30 or 40 seconds or so. If there's no questions, I'm gonna go grab a little bit of an early lunch, and then I'll see you guys at 1 o'clock. Again, once again, thanks for spending time with us. It's it's a weird time. These workshops are something I enjoy doing. I really enjoy getting in front of the customers. Again, I did a workshop at Ohio State. I forget how many years ago. Very good experience. Again, getting in front of customers and talking. And honestly, I miss the one-to-one, the little kind of questions that pop up from end users about their problems, because it helps me understand again the problems that you're having with your samples, and it also helps me understand what you're researching and where research is going, because in the end we want to be one step ahead of you guys, but often we're one step behind. So if we can be a step ahead of you, it's even better. So okay guys, I will then see you guys in about an hour for our Ask the Expert session. Again, thanks for having me.